Good afternoon and welcome to the second talk in the IISc Colloquium series for this year. I'm very happy to introduce the speaker today. This is Professor Vijay Natarajan. Vijay received his PhD in computer science from Duke University, and he holds a PE degree in computer science and an MSc from BITS Pilani. His research interests include scientific visualization, computational geometry, I like that very much, and computational topology. In current work, he is developing topological methods for time-varying and multi-field data visualization and studying applications in biology, material science, and climate science. And the title of his talk is Topological Descriptors and Scalar Field Visualization. Vijay, please.
So thanks for the opportunity to share with you some of the highlights of our research. So this is essentially research conducted within the Visualization Graphics Lab. Visualization Graphics Lab, or VGL, focuses on the development of algorithms and the study of topological structures. So we design and develop algorithms to compute these structures, to store these structures, to query using these structures, to compare them, and to display them. All motivated by the need to understand patterns in data and to explore data. So as a part of that, there are multiple themes of work within the group, and I'm going to be following one of those themes and presenting that to you in today's talk. But before I begin doing that, let me start by first acknowledging all the great work that was done by the team, right? So all the work that I present couldn't have been done without the inspired work of all the students, both current and past, all the research staff, and the postdocs and the interns. I'll try to acknowledge all of them again towards the end, but I wanted to first do this before I begin discussing any of the works. So my aim is to discuss, highlight some of the research that happens in the group. And by way of introduction, let me just unpack the title. The title had two words, scalar field visualization and topological descriptors. Let me start by talking about them. Visualization. So let's try to answer the questions: what, why, when, who, how, and so on. So here is a definition of visualization. Computer-based visualizations, that's of course the focus here. There are other kinds of visualizations as well. Computer-based visualization systems provide visual representations. So the aim is to create a visual representation of data. And these representations are designed to help humans, to help people carry out tasks effectively. So a visualization discussion always has a human in the loop. This is kind of an assumed, right? So the visualization is meant for humans to carry out specific tasks. So when do we need visualization? When do we care about visualization as a way to understand data sets and to use as a tool? This is when we would like to augment a human's capability, not necessarily to replace. And this is particularly of value when no automatic solutions exist yet, right? Perhaps an automatic solution is being developed and visualization plays a role, but once the automatic solution comes in, perhaps there is not much use for the visualization. Another situation where visualization plays an important role is when the human needs to understand details, or as a user, we would like to understand patterns in the data, take some decisions and so on. But it's unclear what kind of questions we would like to ask, right? We are not able to articulate those questions very well. So the process of exploration helps articulate those questions. So that's another place when visualization comes into play. So clearly visualization is a visual presentation of data. Numbers are a good visual presentations of data. I do not have a beautiful mind to find the patterns here. Perhaps some of you do. For me, this is a more useful visualization that shows some of the structure in this virus. This is also a visualization, perhaps of use to someone, right? Another example which tries to drill down this point is maps. We all use maps, which is essentially a transformation of the geography of the Earth, modeled typically as a sphere, transformed onto the plane. Different tasks require different transformations, different maps. A political map is one such as shown on the left, where the area is preserved and is of use when we would like to understand political boundaries, when we would like to take decisions regarding anything that concerns politics or geography and so on. On the other hand, navigation, where you would like to chart courses either on a ship or on a plane, require maps that preserve angles, such as what is shown on the right. This is called the Mercator projection, which is a conformal map that preserves this property, but clearly does not preserve area. All you have to do is compare Africa and Greenland, and you already know that area is not preserved. So clearly the visualization depends on the task at hand. Why visualize? Well, as humans, we have evolved to recognize patterns. Our cognition system, especially the visual cognition system, is highly evolved to identify patterns, to identify when there is a predator and so on. So we would like to leverage that capability to understand patterns in data. And often these patterns are better perceived by humans in 2D. But that's not the answer I want to give here. The answer I want to give here is why visualize, why talk about visualization, because there are a lot of applications that will benefit from visualization. And let me list some of them by categorizing them based on the type of data. Spatiotemporal data, such as data that coming from imaging devices, data coming from simulations, or data coming from sensors and so on. This is going to be the topic of today's talk. I'll come back to this. Another class of data is all your beautiful Excel sheets, right? So tabular, columnar data that comes from in business analytics, sports analytics, whatnot. High dimensional data that is increasingly becoming something that everyone's studying now. Typically represented as point clouds in some high dimensional space, often a Euclidean space, not always so. And in the high dimensional data is often not clean, it has noise, so there are automated techniques that allow you to identify the noise, but you may want to see patterns in the high dimensional data, such as clusters, understand the relationship between these clusters and so on. So that's another class of data. Data where relationships are important, such as social networks, graphs, networks, or structures where hierarchy is important, as modeled in a tree, right? So this kind of data also requires visualization in order to answer different queries and in order to perform different tasks. So a wide variety of visualization applications. I am going to focus only on spatiotemporal data, and that takes me to the next question: how? Right? How do I visualize? Let me talk about the spatiotemporal data just a little bit, just in order to kind of specify what I mean by spatiotemporal data. So here you have visualizations of different kinds of data coming from imaging devices, such as on the left, you see data from near infrared microscopy or electron microscopy of a virus, and followed by data from a CT scan of a human torso. All of these are represented as some kind of intensity values over a 3D volume, or data from material science, the study of pores or the study of the large-scale structure of the universe. These come from simulations, again over typically a 2D or a 3D space, potentially time-varying. So the data in many of these applications can be represented as a scalar valued function. And that's the abstraction we are going to work with. We are going to work with scalar fields, so essentially a scalar function defined over RD, so a d-dimensional Euclidean space. And we'll talk about visualization for such scalar functions. So how do I visualize a scalar function in 2D? Isocontours are a popular technique. An isocontour, to be specific, is the pre-image of a scalar value. So if I have a height map, each of these red curves is an isocontour because it is the collection of points at a given elevation, at a given height. The collection of all these isocontours gives you a good indication of the topography of the elevation. This technique extends to higher dimensions, not always very nicely. So the collection of isosurfaces for a 3-dimensional scalar field could be really complex. There will be a lot of clutter, it makes it difficult to understand. But that doesn't mean it's not useful. There are many instances when isosurfaces are of value. They capture features of interest, such as the skin structure or the bone structure from a CT scan. Often you do not want to restrict yourself to just some surface features, but you would like to see the entire volume. And this is also possible using a technique called volume rendering, which judiciously uses color and transparency to show features that are of interest in an entire volume by synthesizing an image. This also has limitations. As the number of features becomes large, you have to carefully fine-tune the color transparency in order to generate a view that is of value. So this is, by the way, those of you who recognize, this is from the, well, old now, Millennium simulation of which was doing a lot of rounds on the newspapers those days. So the takeaway here is that these techniques have been studied for a long time. These are called classic visualization techniques. They continue to be of use, but they do not scale well as the data becomes large and as the data becomes rich in terms of features. So that brings me to some of the challenges in visualization and in visualization research. So of course necessitated by the size of the data and the richness in terms of features, number of features and the variety of features. For example, in the large-scale structure of the universe, a volume rendering does help you see some of the structure, but it turns out that my understanding, at least a computer scientist's understanding of this very deep physics, is that the what is of interest is the filament-like structure and which act as highways, and the halos or the clusters which are the home for all the galaxies. Those are of interest, and those appear at different density regimes. And it's very difficult for you to use color and transparency to show all those density regimes, and which is why a volume rendering typically fails. So it's important to be able to extract these structures explicitly and then have a way to visualize those computed structures. the problem becomes even more difficult to handle when the data changes over time, or when you have ensemble data, which is, for example, you run a simulation and you run it over different choices of parameters. So you get a collection of data sets. That's an ensemble. So visualization becomes all the more challenging for such scenarios. So one approach towards addressing this challenge, there are many. One approach is integrating existing analysis techniques, maybe newly developed analysis techniques, together with the visual aspect of the analysis. What I'm going to talk about is the computation of visual abstractions. So in the case of the universe, this would be extracting the filament-like structures using topology, naturally, and then displaying those structures by providing additional capabilities for simplification, for querying, and so on. So the computation of these topological structures also make this visualization amenable to like comparison-driven analysis. So you can compare two structures, look at where they are similar, where they are dissimilar, and so on. Let me give you a quick example as to where we can see the need for a topological structure. So on the left here, you see a volume rendering of the human torso. This is a decent volume rendering, quickly generated. On the right, what you see is a tree. We will define this tree later in the talk. Individual arcs in this tree correspond to anatomical structures that are of interest. So you can think of the tree as an abstract representation of all the features in the volume, and selecting individual arcs allows me to select those features of interest, and I can use this selection to highlight those features in the visualization you see in the middle, where the individual organs, the lung, the bone structure are highlighted within the same volume rendering. So that's one of the application of such a topological structure, the highlighting the features that are of interest, right? So what do I mean by topology? What do I mean by topological structures? Let me try to unpack that a little bit. Topology is the study of how space is connected. It's difficult to introduce topology without this picture, where we say the coffee cup is the same as the donut. Of course, terms and conditions apply. So the study of topology dates back to the study of by Euler on the 7 bridges of Königsberg problem. There are the way topology is actually studied from at least a perspective of today's talk is via invariants. So you study spaces by looking at invariants and using them to decide when two spaces are equivalent or when they are different. A simple invariant would be number of connected components. If you have two spaces that have different number of connected components, then you know for sure that they are different. Another invariant would be the number of holes or tunnels, or for a 3D space, the number of voids inside. All these kind of named invariants can have mathematical representations. For those who know, Betti numbers, homology, homotopy, if you want even stronger homeomorphisms, diffeomorphisms, and so on. So what we would like to do is to study topology by representing some of these invariants. For us, a popular, kind of a useful representation is homology groups. I'm not going to introduce them formally here. I'm going to give more intuitive kind of introduction to all these terms. Right? As always, terms and conditions apply. So a coffee cup is always not just a coffee cup. Coffee makers do make different kinds of coffee cups. So there is noise in the data. There are other designs. But the bakers are also not far behind. They also have equivalent structures. For those of you who know the Bretzel, these are all German, thanks to my recent visit to Germany. So how do you use topology, right? So what is topological data analysis? So we try to use topology by bringing in the study of connectivity of space to understand the shape of data, right? So the data here is typically a point cloud or a scalar function. And by a shape of data, I would mean, for example, the number of components or clusters in this point cloud, which is difficult to identify when there is noise. It could mean the number of loops or empty space, right? So the cycles in the data. Can you recognize that even when there is noise? The number of branching structures in your data. Can you identify that when there is noise, right? So this is what I mean by shape of data. And again, we already talked about shape of data in the context of these scalar functions. So the focus is on more an algorithmic and a computational perspective. And it's based on ideas from algebraic topology, homology, and Morse theory. This is a kind of a very new, vibrant community. There's a lot of conversation between computer scientists, mathematicians, and statisticians, not to mention people who own the data, right? To scientists, engineers, social scientists, etc. So within our group, we kind of take a holistic approach towards the use of topology or TDA in general, together with visualization. So we have worked and we have results at the theoretical foundations, looking at what is called kind of PL extensions of these the ideas called from discrete Morse theory. Constructing some of these topological structures like that tree that I showed you. Some of the names that I'm going to talk about later are contour tree, Reeb graphs, Morse-Mail complex. Designing fast algorithms with provable guarantees in terms of the quality, in terms of runtimes, in terms of memory required. Efficient implementations using or leveraging the multi-core or the GPU capabilities that we have now. Building libraries, software that can be used by others, and of course, practical analysis pipelines to get in close collaboration with application domain scientists. So we have projects across the board. So my aim is to talk about one topological structure at some length, and then a little bit about a second topological structure, so that there is some flavor of what a topological structure looks like. So that's what I'm going to do now. And in order to do that, I have to introduce some preliminaries, right? So these are fairly simple. I can, but I would like to present the notation anyway. So we are dealing with a scalar function. So a critical point is one where the gradient goes to 0. We talk about the stability of such a critical point. Intuitively, at least if you think of this 2D scalar function, let me try to talk about stability in the context of, let's say, the local minimum that's at the center of the domain, right? So that's marked by this gray point. So if I'm at this minimum, if I perturb this point a little bit, right? And if it's under the influence of gravity, so gravity acting in the downward direction, does it return back to the minimum, right? And in how many independent directions can I perturb the point such that it returns back to the minimum, right? So that's a notion of stability. Formally, this is the number of negative eigenvalues of the Hessian, for those who already recognize that. So the Hessian test, which is essentially the matrix of second derivatives, that tells me whether the critical point is degenerate or not, right? So if a critical point is degenerate, then let's set that aside. If it is not degenerate, if it is generic, then the number of eigenvalues which are negative gives me a way to talk about different types of critical points. So a minimum is one which is stable in all directions. So there is 0 degrees of instability. So I call it a critical point with index 0. The maximum is one which seems to be unstable in all directions. So 2 directions here. So it has an index 2. And the saddle, which is the other kinds of critical point you see there, has index 1. So we call f to be a Morse function if none of its critical points are degenerate. So we kind of wish away all the degeneracies, right? And this is not a bad assumption, by the way. So one can show that that this is actually a good assumption in practice as well. So Morse theory, so we talked about Morse functions, which is studied in a branch of topology called Morse theory. Morse theory studies the relationship between the connectivity of space and functions defined on top of them. If I take f to be a function defined on a manifold, such as a sphere or a ball or a circle, so M is one such surface, f is some scalar valued function. Assume that it is infinitely differentiable. For practical purposes, second derivative is what we need. A point is regular if the gradient is non-zero, and it is critical if the gradient is 0, right? So again, it's regular if the gradient is non-zero and critical if it's 0. However, in practice, we do not have smooth functions. We have functions sampled over the domain, and the domain is represented often as a sample and potentially represented for something, for example, using a triangulation, right? A piecewise linear approximation of a smooth surface. The function, of course, is also represented as an approximation sampled at vertices and linearly interpolated within the elements. So it's a piecewise linear function. The notions of regular and critical points can now be extended thanks to work by Banchoff in a way that avoids numerical computation. And this is really it. So a regular point, so without looking at gradient, if you look at the behavior of the function in the neighborhood, so neighborhood is represented by this term link LK. So the link of a vertex is the collection of vertices that are adjacent to it together with the edges that connect them. So essentially the ring-like neighborhood is called the link. The lower link is the collection of vertices that have function value lower than the vertex at the center. That's shown in solid. So if the structure of this lower link can help me classify the types of critical points. And this is purely a combinatorial procedure, no numerical computations required. And this works for critical points as well. So just kind of a pictorial representation of what this lower link looks like. So you can imagine that the lower link of a minimum is empty. So all the neighbors have value higher than me. So the lower link is empty. For a maximum, all my neighbors have function value lower. So the lower link looks like the circle, also called the one sphere. So this is essentially kind of a sample of the approach taken towards using some of the ideas from Morse theory in the piecewise linear setting. By transporting all the numerical computations to combinatorial computations, we are able to compute these structures efficiently. So let me first define the first structure, which is the Morse-Smale complex. So with the same example, let's look at the so-called integral lines. So an integral line is this maximal path as shown on the left, whose tangent at every point aligns with the gradient, right? So if you are at any point, if you keep tracing the gradient and walk along, then you get the integral line. So naturally, the endpoints of this integral line are critical points where the gradient goes to 0, right? So there is an origin and there is a natural destination. So what is shown in the figure here at the center are the collection of integral lines whose origin is a given minimum and whose destination are all over the place, right? This collection of integral lines is called the ascending manifold. So in this case, it's a surface, right? So it's a 2 manifold. Similarly, one can define a collection of integral lines that terminate at a given critical point. This is called the descending manifold. Quickly looking at the descending manifolds of all 4 maxima that you see there, you see that there are 4 descending manifolds and they partition the domain, right? Similarly, the ascending manifolds also partition the domain. Now, if I overlay one on top of the two, overlay the two one on top of each other, then what I get is a partition into monotonic regions. So the region in what shows up as brown is a collection of integral lines that share a common origin and a common destination, right? So that's the region here, right? They share a common origin, which is the minimum, and a common destination, which is the maximum. So these are monotonic regions, in the sense no critical points in their interior. And this decomposition is called the Morse-Smell complex. And this decomposition can be stored using a combinatorial representation, which was developed much earlier in a different context in geography, but made mathematically formal by Stephen Smale, and then extended to the piecewise linear case about 20-25 years ago by Edelsbrunner et al. So the combinatorial structure of this Morse-Smell complex consists of these quads that you see, the brown quads, their boundary arcs, and the boundary of those arcs, which are the nodes that are the critical points. So this combinatorial structure is now my topological structure, right? So that's what I call as a topological descriptor. It abstracts away all the geometry, right? And it allows me to, it produces a reduced representation of my data, of the entire scalar function. So this allows, for example, to do controlled simplification. So a 1D example probably helps. The function on the left can be simplified by cancelling a pair of critical points, in this case a minimum and a maximum, resulting in a smoother function, right? This idea works in all dimensions, and that's one of the main lemmas of Morse theory. So I'm just giving you a pictorial representation of that, right? So on a 2D function, you can cancel a pair of critical points. In this case, one of those maxima is cancelled with the saddle that's adjacent to it. That's shown here. This maximum is cancelled with its adjacent saddle, right? Resulting in a new function which has only 3 maxima. So this controlled simplification is now possible, and think noise removal, right? This allows for a controlled mechanism to remove noise in your data. And that's one of the important powers of this topological descriptor. This entire step, even though it's intuitive, can be formally stated, and there is this cancelling Handel's lemma, which actually states this by saying that critical points can be created or destroyed in pairs, resulting in new Morse functions, if the critical points differ in index by 1. So a maximum can be cancelled with only a saddle, and a minimum can be cancelled only with a saddle. A max min pair cannot be cancelled for 2D functions, right? So the notions of critical points, their definitions extends to 3D. Let's not look at all the details. The min and max are recognizable. What I show here is the lower link. So for a min, the lower link is empty. For a max, the lower link is this entire spherical shell. And again, these ideas can be transported to the piecewise linear case. A lot of this was done early in the 2000s, setting the stage for computing the Morse-Mail complex. And since the early 2000s, for about 10 years, there were many algorithms designed to compute the Morse-Mail complex. Numerical accuracy was one of the main issues that they tried to address. Because even if you are able to compute the critical points without numerical computations, the tracing of the gradient lines is numerical in nature, and it was difficult to handle that effectively. So that was one of the series. That's where we stepped in. We talked about how one can model this entire problem by rewriting the Morse theory and the critical points computations and the gradient line tracing in a discrete setting where a gradient is no longer a numerically computed quantity, rather it is represented as a pair, right? So let me again use pictures to help explain this. What you see on the right is a 2D scalar field, and you see gradients on them, I think downward gradient, so it's kind of the negative of the gradient. So ideally we would like to trace these gradients as you go down or up, right? So these can be modeled as pairs between vertices and edges, or between edges and faces. And now tracing these gradients is essentially tracing paths, which is a collection of these pairs. So critical points, remember critical points are where the gradient is 0. The equivalent of those critical points is a cell here which is not paired. So a maximum now assumes the role of a maximum is now actually handled by this cell, 2D cell, right, which is shown in red. A saddle is now represented by an edge, one which is not paired. All the others are paired. So this vertex is paired with an edge, so it is a regular point, right? So gradient line tracing is now path tracing in a graph. And so the MS or the Morse-Mail complex construction works in 4 steps by identifying these gradient pairs, by locating the critical points, all combinatorial, computing these connections via path tracing in a graph, and computing these connections again from maxima to saddles, minima to saddles. 3D brings with it some complications, so you have to talk about these saddle connections. So that's a technicality, I won't talk about it here. So this transformation from the piecewise linear to this discrete setting allowed for fast algorithms. In particular, it allowed for fast parallel algorithms. What we showed was a way to compute these pairs, gradient pairs, such that the gradient pairing in a particular cell is independent of the gradient pair in the neighboring cells. And this independence, proven in the form of an independent pairing lemma, allowed us to compute these pairs in parallel. So, the typical pipeline for computing the Morse-Mail complex was from the top left. You take the domain, you partition it into pieces, and compute the Morse. Assume that the Morse complex is computed on each partition, and on the boundary you populate all the cells by artificially tagging them as critical, and so then when you merge the adjacent segments or the adjacent blocks, you merge them via a cancellation procedure, which pairs critical points and cancels them. By rewriting this entire path tracing as a sequence of cancellation operations, we were able to write down a parallel algorithm. And this was the first known parallel algorithm for this Morse-Mail complex. And in subsequent work, we were able to show efficient GPU and efficient GPU-CPU hybrid implementations, which resulted in some fast software libraries. One that is currently functional from our group is called PyMS3D. Again, subsequent work allowed us to extend this to a GPU-only implementation by rewriting some of these path tracings as matrix operations and using the power of the GPU to perform matrix operations. We also looked at application-specific needs. So the entire Morse-Mail complex was not always required. We needed a subset often. This is one such subset was called the extremum graph, and we recognized the need for computing such a graph, and we could compute that using a specialized algorithm. So that was more recent work a couple of years ago. Several applications of the Morse-Mail complex. I want to talk about just one application, namely to the study of granular materials via a tool that we call MorseGram. Granular materials like sand and powder and beads and so on have very complex behavior that are neither solid nor liquid. And one of the ways to study them is via imaging them using an X-ray CT, of course 3D. So MorseGram provides visualization capabilities for studying these X-ray CT data using, of course, the Morse-Mail complex for abstract representations. Under the hood, it uses PyMS3D and allows for post-processing and statistical analysis as well. So here is one of the results from MorseGram applied to a granular ensemble. What you see in the center is that the segmentation that is computed using the Morse-Mail complex avoids so-called over-segmentation, which is the bane of existing methods like watershed, which is heavily used in this literature. So individual grains or individual particles have to be segmented as one and not over-segmented. Under-segmentation is also a big problem in many cases, and that's also handled very well by MorseGram. MorseGram supported and is continuing to support statistical analysis of cemented sands by computing various contact statistics, the coordination numbers, things like that, allowing for localized exploration of individual particles and its neighbors, allowing for the computation of the entire contact network and supporting force network analysis on this network, and more recently on breakage analysis when this entire granular ensemble is under a compression load. There are many other applications that where we have shown the use of Morse-Mail complex and either built tools or provided analysis solutions. Like I mentioned, one was the structural analysis of the universe built into a tool called Felix. The analysis of pore structures in, for example, a copper foam, and extending that to more recently towards the study of pores in zeolites, essentially looking at classification of different kinds of zeolites. The tracking of these upper atmosphere wind patterns called Rossby waves that affect long-term or long-distance weather patterns. For aligning molecular surfaces using a tool called MS3 Align, and a few others. But I would like to kind of end with that in terms of the Morse-Mel complex, and maybe within the next few minutes talk about another topological descriptor and conclude. A second topological descriptor that we have studied extensively is called the contour tree or the Reeb graph. And here is essentially the definition pictorially. So, I'll also give the formal definition. So again, a scalar function defined over a d-dimensional domain. For illustration, we show an interesting domain together with a simple height scalar function, which is the height above the surface. And what is shown is on the domain you see the level sets or the isosurfaces, right? So clearly the number of components of this isosurface changes as you sweep up the domain with increasing values of the scalar. The Reeb graph tracks the evolution of these connected components of the level set. So formally, the Reeb graph is the quotient space under an equivalence relation. And the equivalence relation is one which says two points are related if both belong to the same level set component. Right? So, so the Reeb graph is, again, it's named after a mathematician who worked with this 50, 60 years ago. Constructing the Reeb graph is a big problem. There is a loop-free version of this called the contour tree. And if the domain, one can show if the domain has no loops, then the corresponding topological descriptor also has no cycles. And that's called the contour tree. This allows us to capture features of interest. So new components are born new components are born at, for example, minima. A new component of a level set is born. Two components merge when you hit a saddle. And we talk about that as the death of one of the components. We let the younger one die. Must be why. But so the older one persists. It's called the elder rule. This allows us to pair birth and death events, and this is called a topological feature. And this pair is also called in the literature as a persistent pair. And it corresponds to a homology class, for those of you who can recognize what that means. Right, so computing the Reeb graph is also an important problem that has been studied over the past 20 years. And we have made several contributions on this front, beginning with an optimal algorithm or near optimal algorithm that the optimal would run in n log n time, where n is the size of the input. This was at that time the theoretically best known result. Subsequently, an optimal algorithm has also been designed by others. But we were, of course, not happy with this near optimal algorithm because it was hopeless in terms of an implementation. So we designed a so-called output sensitive algorithm, one that needs more time if the output is large. It doesn't, of course, depends on the size of the input, but it would give you produce a result quickly if the output was small. And this turned out to be very fast in practice. Driven by the need to use the multi-core resources available, we had a parallel algorithm, or the germination of a parallel algorithm, which split the input into small pieces. And if you can see there, it split the input into small pieces such that each piece had no cycles, and computed the Reeb graph or the contour tree within each component and stitched them together. So this split and compute approach was based on a lemma that we were able to prove in terms of like where do you split these cycles. That's called the loop saddle lemma. And this resulted in significant speed ups up to 100 times and was at that time able to handle 4 to 6 million elements. Subsequently, for contour trees, we showed that we could handle up to 8 billion vertex data within a few hundred seconds. So what this essentially meant was one could now extend topological analysis to large size data, because computing the topological descriptor was no longer the bottleneck, and it allowed for different applications. So I will not talk about different applications. I already talked about this application. The tree that you saw on the right is the contour tree, right? So it allows for feature-directed visualization. It also allows for computing symmetric structures within scalar fields, such as what we saw in the first couple of slides for this human adenovirus. It also allows us to find symmetric regions or symmetric structures in scalar fields from different applications, from the buckyball structure to data from flow simulations and so on. So many other applications that range from symmetry identification to cyclone tracking to summarizing vortices in a fluid, towards tracking clouds and identifying rain events, and finding periodicity in time-varying data. All of these are powered by the contour trees that I talked about. And each one was kind of conducted in close collaboration with a domain scientist who helped us both provide the problem at hand and also validate the solution, so that each one was a long process. So I want to highlight that aspect, because none of these applications would have been possible without the expert input from the scientists, both from within IISc and outside. All these were wonderful collaborators. So that brings me to the end. I would like to thank all the agencies that supported this work. Most recently from the Humboldt Foundation, and I'm one of their ambassador scientists from next week, so I should especially call that out. So if you are interested in one of these Humboldt fellowships, then come and talk to me. I'm happy to discuss that. This was, of course, not possible, like I said, without the work of a large number of researchers. A couple of them are here, thanks to them. And of course, with all collaborators, again, some of you are here. Thanks for coming to the talk. I'm not going to list all of them, but they come from different departments within IISc, and from some who were at IISc and now have moved on to other places. They were faculty here and moved elsewhere and so on. So thanks to all of them for all the input. Some of the collaborators are still here, and I'm looking forward to more discussions with them. So the outlook is that the data continues to be large in size and feature rich. So new paradigms are needed for exploration, and I continue to be interested in applying topology-based methods for exploring these data sets with a specific focus on time-varying and multi-field data and applications to material science and to oceanography. So that's some of work with Vinay Chandran on the lower right. This is an ongoing collaboration looking at the salinity in the Bay of Bengal and studying its movement. And on the top right is again the data from Tejas from Civil. That's also an ongoing collaboration where we study the contact networks from granular ensembles of sands and beads and so on. So with that, I thank you again, and I'm happy to answer questions.
Thank you, Vijay, for the fantastic talk. Questions?
Yeah.
homology.
Yes.
How does that help?
Okay, so persistent homology is the study of homology under a filtration. And the filtration was what I tried to show via the sweep. In the context of scalar function, it's the sweep, but you can define it for a generic simplicial complex. You can continue to talk about the persistent homology classes, and that can be coded as a so-called barcode, a persistent diagram. And that is used as a feature descriptor. I think there are now pipelines that take those descriptors and into your standard machine learning pipeline. So people have started using them now. Yeah. Yeah.
Just wait for the mic.
Yeah, hi, just curious. So my understanding is everything is purely topological. The geometry doesn't play any role at all. There's no...
No,
or is there some... so for example, in some of this work on contact classification and say identifying things that could potentially come into contact, right? Yeah. So there is some topological things there, but there's also an influence of geometry, right? So do you worry about those kinds of things at all? Because what you showed were just skeletons and structures and like throwing all the geometry away.
Yeah. It's a very good question. While I did say that I throw all the geometry away, a lot of the interesting questions are posed in terms of the geometry. So the topology is useful in order to compute this abstract representation, but you can think about annotating this topological structure with the necessary geometry. For example, with the Morse-Mel complex, you have this skeletal structure. I could encode each quad with the area, just a number, right? And I could use that to decide what is noise, what is not noise, and so on. I did not store the exact geometry. So just as an example. So geometry is definitely, and I cannot avoid that. It's definitely needed, but I can annotate. Yeah.
Thank you for a nice talk, Vijay. I wanted to follow up on the question by Narayan.
Yes.
I didn't see any length scale in your pictures. Does it mean that you're not terribly worried about how lengths and dimensions and stuff? Or, for example, you could say I could put kilometers or meters in your pictures. You still get the same result, or it is gauge variant?
No, that's a very good question. So the construction of all these structures and the simplification are both coordinate free and scale free. So that is actually touted as a power of this approach, that one can compute structures irrespective of the scale. But when scale is important, we have to bring it in, and we do bring it in some cases, right? But post computation of the topological structures. So for example, in the granular ensemble, we would care about the actual size of the grain and use that to take some post-processing decisions, right? But that's not something I would do. That's what the domain scientists would do. Yeah, but I would provide them with that information.
That's a nice talk. So you're assuming that the scalar field is already computed and given, right? So there are some contexts I can think of in terms of, say, optimization questions, where you're given, let's say, an oracle that can evaluate a function for you for certain choice of parameters, but it may be a high-dimensional space in which you want to maybe percolate down. Are there ways of actually sort of judiciously actually sampling the scale field while you want to look at the persistent topological structures?
It's a very good question. Something that I looked at about some of the early works on contour trees. We tried to extend it to so-called higher order interpolants, where exactly like you said, you have a partial differential equation that will tell you what is the solving that will tell you the value of the scalar at a particular point. But how do you decide where to sample? I don't have a good solution good answer to your question as of now. There are a couple of results. there is this work on, more recently, about 2-3 years ago, on progressive computation of these structures, right? So the way it works is that it uses the topological structure as an indicator of how well you're converging. So you can use that to decide how to, whether you want to sample more or not. I will have to check if it also helps you decide where to sample, as in with some precision. It will tell you the area where you want to sample. With what precision, I'm not sure. I have to look at the works. But yeah.
Just to follow up on that question, that was one of where you have an oracle that tells a function. But what if your function is noisy? What happens to your properties, topological properties? Are some that are destroyed, but destroyed dramatically, or maybe just perturbed? Right. And also, does geometry help when there is noise? Can you comment on these?
Yeah. So one of the approach, I don't want to say popular, but the more common approach that's taken to noisy data is let me compute all features and then use simplification as a way to remove noise. So if your data has like really a lot of high frequency noise, all of those would be captured as features in the topological structures, for example. And then I can use the size of the feature, which is either the difference in function value, for example, for the contour tree, or it could be if you think of the mountain analogy, it could be the volume under the mountain, or it could be the area of the base of the mountain, or their equivalent. All that can be used to decide if you want to suppress that particular noise or not, right? So in a sense, it's similar to some kind of a filter that you could pass that removes high frequency noise, with the benefit that your noise removal is controlled. So I could say that I want noise to be removed only on one part of the domain and retain the other parts as it is. Or I could say that these are repeating copies of the same data. So however I want to simplify, the top right should be mimicked on all the other components. And this is possible because the simplification is controlled. As in the spatial extent of the simplification is controlled.
You mentioned some features, the perturbation is small, and that's what you're using in some sense to denoise. But are there some features which are very sensitive to the noise that they get destroyed, and so that's not where you should look for denoising? I'm just wondering about some topological features that you're extracting, but they get lost when noise is added.
Okay, so yes, so in fact, often the more often the problem that we encounter is one of spurious noise that is just introduced because of a way of computation. But what you say is will the topology kind of suppress some of the noise when I don't want it to? That's unlikely because I have control over each feature, right? So as long as I take the entire domain as it is without subsampling, and if I assume that the ground truth is the sample that I'm given, and the linear interpolation is as the simplest possible interpolation, captures all the features that I care about. Under that assumption, none of the noise would be suppressed by my topological construction, right?
Thank you. Any other questions? Let's thank Vijay once again.
Thank you.
Fantastic talk.
Yeah, thank you.
Please join us for high tea.